Welcome to physics lecture number 3. Today we're going to be covering some kinematic formulas. So let's dive right in. Here are kind of the 3 formulas that will probably be most helpful to you. First we have kind of a restatement from last time, from lecture number 2, that the change in velocity is equal to acceleration times the change in time. And notice that in both of these on both sides of the expression, velocity and acceleration are both scalars, not vectors. That's because when we use these kinematic formulas, we're assuming one dimension only, or we're operating on individual components. So, for example, in a 3-dimensional system, you'd set up this equation 3 times, one for each dimension of the system. Next up, we have another equation. This equation is not one that we covered last time, and it's one that if you want to derive, you have to use calculus. It states that the change in position, or the displacement, is equal to the initial velocity times time, times the change in time, plus 1/2 times the acceleration times the change in time squared. And this is for if we have a particle and we know its initial velocity and its acceleration, we can compute the distance it travels in some given amount of time. And again, we have scalars on each side. That's because we're working with one dimension or components of a vector. Then finally, we have this other equation. The square of the final velocity minus the square of the initial velocity is equal to 2 times the acceleration times the change in distance times the displacement. And what's good about this equation is that it is independent of time. So if you don't know how much time a process takes, you can still find a particle's change in position or change in velocity, depending on which one you're looking for. And these formulas are pretty limited because, for the most part, they do not use calculus. We do have to use calculus to derive the second formula, but there's some big assumptions going on here. One assumption is that, as I said multiple times, we're only using one dimension at a time. We're operating in components. Either we're setting up the equation for each of the x dimension, y dimension, and z dimension, or we're just in a one-dimensional linear system. And another big assumption is that acceleration is constant. If we use constant acceleration, then this first formula here, change in velocity times acceleration, my pointer is frazzing out, change in velocity equals acceleration times change in time, that formula is valid only if acceleration is constant. As is this formula, which you'll understand if you know where this formula comes from with the calculus, and this formula. So we need to have constant acceleration for kinematic formulas to be valid. And because acceleration is constant, velocity is a linear function, and position is a quadratic function. If you know calculus, you'll be able to understand why that's the case. And when I say linear and quadratic functions, it doesn't necessarily mean that there has to be a t term in velocity or a t squared term in position. All linear functions are quadratic functions where the coefficient of the t squared term is 0, and all constant functions are linear functions where the coefficient of the t term is 0. So let's kind of discuss the situations where we can apply kinematic formulas. Basically, we need there to be constant acceleration, and we need the motion to be linear in the dimension. So, for example, we can treat an object in free fall with no drag with kinematic formulas because its acceleration is equal to g is equal to 9.8 meters per second squared. We know that. It's a constant acceleration, it doesn't change over time. However, let's say we want to take into account the effects of the atmosphere. Atmospheric drag is proportional to the velocity of the object. So that means that as an object's speed increases, the drag force on it increases and the acceleration decreases. So we can't use kinematics to describe that. We need calculus. Let's move on to an example problem. So we have this person, right? And they're on the observation deck of the Empire State Building, and they drop a penny off. And the observation deck of the Empire State Building is 373 meters in the air. So we're going to neglect air resistance, use only gravity as the only acceleration, which means that our object's acceleration is 9.8 meters per second squared. And we're going to find the time it takes for the penny to fall. So to solve this problem, we use the second formula I introduced that relates change in position to initial velocity and acceleration and change in time. And we're going to solve for change in time because all the other quantities in this equation are given. And as you can see here, I basically plugged in the numbers, rearranged the equation, and solved for change in time, and we get 8.72 seconds. Now let's approach this problem from another angle. Here we have basically the same situation, except now we aren't finding the time, we're finding the distance. And you'll notice that instead of giving the time it took to fall, I'm giving the final velocity of the penny. And how I found the final velocity of the penny was with the first kinematic formula. I used the time we calculated last time, 8.72 seconds, and multiplied it by the acceleration, 9.8 meters per second, to find a final velocity of 85.46 meters per second for when that penny hits the ground. And now we're going to use a time-independent formula to find the to find the distance between the bottom of the Empire State Building and the observation deck. And how we do that is with a third formula, the time-independent one. So we know that V initial is equal to 0, V final is equal to 85.46, etc. We plug in the numbers here, we solve for change in x, and we get 372.62 meters. And I said earlier that the Empire State Building is 373 meters tall, so we got very close to the final answer. And the reason for that small 0.38 discrepancy is that we have rounded in a lot of places here. We rounded the final time we found, and we rounded the velocity, and that causes a small change in the answer we find. But all in all, the change is negligible, and later in the course we will discuss significant figures, which tell us exactly where to round our quantities and when we can round them. But yeah, as you can see, this is fully internally consistent, and it's a powerful tool for solving very simple problems. If we want to derive this third equation from the second and first equations, what we can do is we can substitute that V final is equal to V initial plus acceleration times change in time. But yeah, if you know calculus, then it's an interesting exercise to derive these kinematic formulas for yourself. I can't say that kinematic formulas are very applicable in the real world, because in the real world acceleration is not constant, but we will come back to kinematic formulas when it's time to describe projectile motion. Anyways, that's all for today, so thank you for watching this lecture.